Hey guys, so this is sample problem number 4 from the bottom of, I think it should be page 31 for you because it's 33 for me. So it's asking us to calculate the base dissociation constant, the Kb, of the hydrogen phosphate ion. And we're given an original concentration of the hydrogen phosphate as well as a percent dissociation. So we know with those two things, we're going to be able to find the concentration of our hydroxide here, based off of looking at our formula sheet. So remember that Ka and Kb expressions are just equilibrium expressions. So we can actually write our Kb expression here without needing a formula. So we know that we're going to be disregarding this water. Okay, I know that it's in a reaction with water because we're looking at a dissociation constant. So anytime we're looking at a Ka or Kb, we're just looking to see how that acid or base behaves when it's reacting with water only. So in this case, I know that this is going to be acting as my base, the hydrogen phosphate ion, because if I take a peek at my chart, the hydrogen phosphate ion is here, water is way up here, and we know that the strength of the base increases as we move down the list. And so that means that the hydrogen phosphate ion is more basic, so it will be grabbing the proton from the water. So water will be our acid, hydrogen phosphate ion will be our base. So that is reflected here in that the water is losing a proton to become hydroxide, and the hydrogen phosphate ion is gaining one. So I know this is going to be an ice chart problem because I don't have an equilibrium concentration of my hydrogen phosphate ion. So let's start with what we do have. So we know that our initial concentration here is 0.25 molar, and my initial concentrations of both of these species are going to be 0. I know that because my molar coefficients here are 1, 1, and 1, I'm going to have a change here of minus x, plus x, and plus x. And I am going to fill in 0.25 minus x, and I am going to fill in my equilibrium concentrations over here. Now the other thing that I can do off the bat is write my Kb expression. Since I know that Kb is just an equilibrium expression, I can write it with my products over my reactants. And remember, the concentration of each would be to their molar coefficient. I'm not writing any exponents here because the molar coefficients are all 1. Okay, so now I'm set up to solve this. Because I'm given a percent dissociation, I'm going to need to use that to solve for my hydroxide concentration. So on your formula sheet, when we're looking at percent dissociation here, it's down here, it tells you that the conjugate acid over the original acid times 100 is the percent dissociation. So that's for an acid. We're looking at a base, but the same logic applies. So the conjugate base over the original base times 100 is going to give us our percent dissociation. If water is our acid, hydroxide is our conjugate base. So our percent dissociation here is going to be our hydroxide concentration over our original base, which is the hydrogen phosphate ion. Sorry guys if you can hear Aiden in the background, times 100%. So we have this value, we're solving for our one unknown, which will allow us to complete these 3 equilibrium concentrations and therefore find our Kb. So our percent dissociation is 0.080%. This is going to be, in order to remove this, we're going to do the inverse operation, so divided by 100%. And then because we want to get rid of this denominator, we're also going to be multiplying by our HPO4 2 minus concentration, which, just to show you what I'm doing here first, is going to give us our hydroxide ion. Now, I'm going to sub in my value here. So we're actually going to be plugging in 0.080% divided by 100% times 0.25 molar, and I got that value from the question, equals our hydroxide ion concentration. So 0.08 divided by 100 times 0.25 is 0.0002 molar is our hydroxide ion concentration. So now I can use this value to complete these 3 sections in my ice chart, and then I just have to plug them into my Kb expression. So the equilibrium concentration here of the hydrogen phosphate ion is 0.25 minus 0.0002 molar, which is 0.2498 molar. My equilibrium concentration of my products for each one is just my X value, which I've just solved for here. So I can then plug these values into my Kb expression. I'm just writing this squared, as I know that these are created because it's 1 molar coefficient, 1 molar coefficient, 1. When this base accepts 1 proton, it produces 1 of this and 1 of this, which is how I know that I can just square this value because they're produced at the same rate. Okay. Okay, so 1.6013 times 10 to the negative 7. So looking at my sig figs, I have 2, 2. So my final answer is Kb equals 1.6 times 10 to the negative 7.